Hi, this video I want to talk about our PSHA calculations. We're going to talk through some of the ingredients to those calculations, and we're going to do a lot of examples looking at simple cases to try to understand the relationships between inputs and outputs in these PSHA calculations, as well as to understand some of the characteristics of hazard curves and things like that. All right, following along in the book, this is section 6.1 through 6.8, so most of chapter 6 we'll cover with some of the material here. All right, and to get started, we've talked previously about seismic source models and ground motion models. Those are inputs to these calculations. And so what we need to do now is put those together, start looking at these formulations of how everything fits, look at some examples, and understand sensitivity to inputs as well. Sensitivity, I think, is really important here because we're going to have a lot of input models, a lot of parameters to specify, and it helps to understand how could we test which of those parameters are most important, and also when we can start to get some intuition about which parameters are most important, we can focus our attention there in getting those parameters right as we're putting together some seismic hazard study. Okay, so here's a graphic picture of what we're going to be dealing with here. And in the middle, I've got an equation. So this is the actual formula we're going to use to do our hazard calculations. And I tried to annotate up here with some text and some graphics to think through what are the inputs to this calculation. So maybe we can work right to left. I guess let's look at the left-hand side first. So our goal here is going to be looking at, as usual, we'll use lambda for our rate. And we want to figure out what's the rate of a ground motion intensity measure, IM, exceeding some threshold, lowercase im. That's our goal. And we're doing something like the total probability theorem here, but with rates of ruptures instead of probabilities of ruptures. But the layout's basically the same. So we're going to, now let's come over to the right. So our first term here on the far, we've got the rate of rupture I. Right, and so that's dealing with our seismic sources, our seismic source model. And here I've got the picture down at the bottom. Remember we talked about our seismic source model where we're going to have our site and the sources that are surrounding that site. And each of those sources, we're going to need some information about the activity rate of the earthquakes and the magnitude distribution and things like that. So we'll specify out a list of ruptures from that source model and their associated rates. And so that's the source model piece. Now the second, and I guess we could mark that. We could mark that in red here. Then our ground motion model piece is going to be the other term here inside the summation. And so here we're using the ground motion model to predict, given a rupture, which is the rupture we specified over on the right, and given our site properties, the soil properties, and maybe basin properties, things like that, what's the probability that rupture is going to produce an intensity measure value that's greater than that threshold of interest, small im. Right? So the product of those two is going to be the rate of rupture I causing an exceedance of lowercase im. So we'll have the rate of the ruptures in the red, and then some of those ruptures are going to cause an exceedance with probability specified by this blue term. And so the product will be this kind of reduced rate of the ruptures that cause exceedances. That's just for rupture I, though. So then finally, we've got a summation term out front, which is summing over all possible ruptures. Right? We know, depending on how we discretize things out, there could be many ruptures in the surrounding area, and we want to consider all of them. How often do they occur, and what's their probability of causing an exceedance of the IM? Right. We got a couple more graphics up top just to think this through. With regard to this rate of the rupture, we talked previously about kind of magnitude and distance being important characteristics of the rupture, and we can find probability distributions of those given our source model. And so that's reflecting the information in this lambda rup. The ground motion model on the left, that's this form discussed in chapter 4 of the book, where we're going to predict a probability of exceedance of an IM given the rupture properties and the site properties, right? So that ground motion model is coming in the blue term here in the summation. So we can evaluate the red and the blue terms with our source model and our ground motion model, and then we'll just sum those up over all of our possible ruptures. Okay, so that's the schematic idea here. I think it gets a little more tangible when we do some actual calculations. So let's dive into some examples, and we'll build up in complexity here. So the first case, very simple, just to get ourselves thinking a little bit. We've got a fault, and it can only produce one rupture. So that summation over I in the previous slide, we're just going to have one term in our summation here. The site is 10 kilometers away from the fault. This is kind of illustrated over here on the left-hand side. So we've got a distance of 10 kilometers. We've got a magnitude of 6.5 for that one rupture. And we'll say the rate is 0.01 per year. So we've got an average return period of 100 years for these ruptures. Okay? So that's the M and the R are going to give us our rupture conditions. And then we also need a site condition. We'll specify the VS30 as 500 meters per second. So from kind of previous calculations in chapter 4 of the book, over on the right, I'll get us started here. If we're looking at 1 second spectral acceleration and we use the Bohr Joyner-Fumal 1997 ground motion model, we've got those results already for this kind of rupture case. So the mean log spectral acceleration is the log of 0.17 g. Just put it there and with the log showing for kind of intuition. Standard deviation was 0.52. Okay, so that mean and standard deviation, that gives us the ground motion model terms we can use to predict the probability of exceeding any IM threshold we're interested in. Okay, so let's think through the rate of exceeding 0.2 g. So we can say the rate of our IM is going to be spectral acceleration at 1 second. And the rate of exceeding 0.2 g. First, we'll spell out the terms here. So we've got the probability that SA 1 second exceeds 0.2 g given the rupture and the site. We'll have the rate of the rupture. And there's only one rupture here, so we don't have to have the I indices or anything like that. All right, so those were the two terms from the previous slide. We can evaluate them here. So the probability of exceedance, we've got the mean and the standard deviation already. So we can just do 1 minus the CDF, standard normal CDF. And we'll evaluate it at the log of 0.2, which is the IM threshold of interest here. And then we'll subtract the mean of the distribution, which is the log of 0.17, divide by the standard deviation, 0.52. So that's our normal CDF evaluated at 0.2. And then we just have to multiply by the rate of the ruptures, which is 0.01 given in the problem statement. All right. Let's simplify down one step before we combine. So this term in parentheses is 0.378. And that should make a little bit of sense. If the mean of the distribution is a log of 0.17, which that's the median of the distribution in non-log units. So 0.17 g would be the median value we would expect for SA 1 second from this rupture. And we're interested in 0.2 g right now, which is a little above the median. So we should expect this probability to be a little less than 0.5. Okay, and 0.01 is the rate of ruptures. All right, so we get 0.01 ruptures per year, and then about a third of them are going to cause an exceedance of 0.2 g, given the ground motion model, a little more than a third. So we put those two numbers together, and we get 0.00378 per year as our rate of exceeding 0.2 g. All right, so if I'm sitting at my site, I'm worried about 0.2 g, about 0.00378 per year that we're going to see an exceedance. All right, and we just did the calculation at 0.2 g, so which is the x-axis on this plot here is spectral acceleration at 1 second. So we evaluated exceedances of 0.2 g, and we found 0.00378. And so if we plot that point here, it's going to show up somewhere around there, a little higher. That's pretty close. So we're going to get a 0.00378 as our exceedance rate. If we do this again for some other M threshold, we'll get another point. And if we do it over and over again for different IM thresholds, we're going to fill in this whole curve. And this is what we call a ground motion hazard curve. Okay, so this is one of our main outcomes, main products from a seismic hazard study. We've got all the ground motion intensity thresholds we might be interested in along the x-axis, and all the annual rates of exceedance along the y-axis. And then we can go ahead and pick any thresholds we're interested in, or pick any rates of exceedance we're interested in, and read them off a plot, something like this. Okay, so that's our basic calculation. And yeah, I think that's enough discussion for here. Let's add on a little more detail just to think about getting a little more realistic. Now we'll think about an example with two rupture scenarios. The first rupture is exactly as before. The second rupture, we're going to have a larger magnitude at magnitude 7.5 versus the 6.5 on the other case. And we're going to have a smaller rate, only 0.002 per year instead of 0.01 per year. 1/5 is frequent, but a larger magnitude. All right, and the site will be the same, of course. The site is the site. We're just adding in another rupture scenario that might occur nearby. Okay, and both of those ruptures occur on the same fault, so the distance will stay at 10 kilometers. All right, so I'll give you a couple of the pieces here. We won't have to handwrite this all in. But from the Bohr-Joyner-Fumal 1997 model, if we plug in the new magnitude, we're going to get a log spectral acceleration at 1 second of log of 0.45. So the median intensity would be 0.45 g, substantially larger than the 0.17 g from previously. Standard deviation is the same as a function of magnitude with this model. If our calculation we had to do before, the probability of SA 1 second exceeding 0.2 g, now we're going to do it given the second rupture. We will plug in the new mean of the distribution into our probability of exceedance calculation. In this case, the 0.45 g is a lot larger than the 0.2 g threshold we were interested in. So we have a pretty high probability of exceeding 0.2 g given this larger rupture, 94%. Then we'll substitute that probability in to our hazard calculations. Right, so we've got for rupture 1, we had our previous numbers. We had the 0.01 rate per year of ruptures times a 0.378 probability of exceedance given that rupture. With this new additional rupture, we've got a rate of 0.002 per year. So we'll put that into our formula. And then our probability of exceedance of 0.94, we're going to multiply that by that rate. Okay, so we've got a rate times a probability plus a rate times a probability. All right, we're doing the summation over all the ruptures now, but we've got 2 ruptures, so there's just 2 terms in that summation. We've got the individual products. The 0.00378 is the same as previously. And now we've got an additional 0.00188 from this rupture 2 rate per year of exceeding. So now we've got a total of 0.00566 per year of exceeding this 0.2 g ground motion. Right? So with the additional rupture occurring on occasion, we've got an increased rate of exceeding 0.2 g. Okay, we can look at this one graphically as well. I've got all the numbers spelled out in this table here, the same numbers as the previous slide. But let's look graphically. I think this is the interesting part, maybe. If we look at 0.02 g, it's down here on our axis with our hazard curves. And I'm going to trace this line up, and we'll think through what we've got here. So we've got, now, from this ground motion hazard curve plot, I've got the results from just rupture 1 in red, the results from just rupture 2 in the light blue, and then the total hazard in the darker color here. So we've got, from the previous example, we've got the 0.00378 from the rupture 1. Now we're going to add to that an additional rate of 0.00188. If we add those 2 up, we get to the 0.00566 number that we came up with, right? So graphically, the individual ruptures hazard curves are getting added up to get up to the total hazard here, okay? And so we can see how those numbers fit together for this 0.2 g. If we repeat this calculation for other thresholds, we can get the additional numbers drawn in here. The 0.05 g case is in the book if you want to look through at another result. So I've got that number just plotted out here for the total hazard. But a couple things here we can see is that if we go over to the very far left, the hazard curves are all flattening out. So these are very low amplitude spectral accelerations. And so as I get lower and lower, I'm not getting any increased rate of exceedance over here. And so it turns out as I go to very low spectral accelerations, it's basically probability 1 that I'm going to exceed those thresholds if I get an earthquake, right? And so the intercepts over here on the far left are just the rate of the ruptures, right? So rupture 2, we had the rate of, I'll try it out a little bit more, 0.002 per year of the ruptures. That's actually the value that the hazard curve plots in at here. Because if I get one of those ruptures with a rate of 0.002 per year, I'm basically certain to have exceeded this 0.05 g, or 0.05 g spectral acceleration. And then if I come up to the red curve, remember my rate of ruptures here was 0.01, and I'm basically at 0.01 as well. So we can see down here, maybe I'll add a little label, that the probability of exceedance given the rupture is about equal to 1. Right? And when I add up all those results for this total hazard case, that number there is generally, it's about equals. It's about equal to the sum of the rates of all the ruptures. So sometimes that can be a useful check of like, how high is that number over at the far left? Like, how often do I see earthquakes overall at this source or at this site? Okay, so that's one interesting observation we can make starting to look at this plot. Another thing we can see is that kind of over on the right, at these lower intensity levels, the red line from Rupture 1 is a lot higher than the light blue line from Rupture 2. Right, so Rupture 1 contributes the most. And that's because at these low IM levels, any of the ruptures have a pretty high probability of causing an exceedance of that IM level. And Rupture 1 it's much more frequent, right? It's got 5 times the activity rate of Rupture 2. And if they can both produce an exceedance, of course, the active one is going to have the most contributions to the overall total hazard. Right? So the red curve is pretty close to that dark blue curve. If we go over to the far right side, we get a different story here. So out here, my shape a little different. Nice. All right, so out here, the red curve is much lower now than the light blue curve. And the light blue curve is basically the same as the total hazard. Note that because we're in log scale, the kind of additive nature of these curves may look a little funny to you. But as that red curve is getting down really low, it's a 1/10 of the value of the light blue curve here, just given the log scaling. And so adding in the red curve is not really moving the total hazard much up above the light blue curve. So stare at that for a second. It might look a little non-intuitive at first, but we are adding up numbers here. Okay, so over here, we'll say Rupture 2 contributes most. And that's because Rupture 1, even though it had all that extra activity rate, it was 5 times more active. What's happening is that the probability of SA 1 second greater than X given Rupture 1 is pretty close to 0. So Rupture 1, because it's that smaller magnitude event, had the smaller mean value of the IM, or the log IM, then it's got a pretty low chance of causing these exceedances of like 1g spectral acceleration, versus Rupture 2 has a much better chance of causing an exceedance, much higher probability. And so with that low probability, its contribution to exceedances is pretty low. All right, so those are a few intuitive things that we can note as we look at this real simple case. As we get a little more advanced, these types of observations hold, but they get a little trickier to point out. So I like starting with these really simple cases here to build some intuition. Okay, let's go to a little bit more advanced case. So now we're going to think about the source with the Gutenberg-Richter magnitudes. So here I'm following the same parameters as earlier in the book, where we had the source 10 kilometers away, Gutenberg-Richter magnitudes truncated between 5 and 8 for magnitude, p-value of 1, and then 0.05 ruptures per year that are bigger than magnitude 5. Okay, so just repeating out some of the pieces that we had in the previous examples. Okay, so we've got this table here of magnitudes going from 5 to 8, and I've got them discretized by 0.2. And we have the rate of rupture I, which in this case, because magnitude is the only thing varying, the distances aren't varying, this is just going to be the rate of magnitude I. So we want to know how likely that magnitude is. Okay, and the way we'll do this is we'll discretize ourselves up and say the rate of magnitude equaling 5.1 is going to be the rate of magnitude greater than 5 minus the rate of magnitude greater than 5.2. Okay. And we'll do this for each increment and say, if we have all these exceedances, we'll take some intervals of magnitude, and the difference between those two rates will be the rate of magnitudes between 5 and 5.2, and we'll just assign that all to magnitude 5.1. Okay. And so we do that stepping down through all these rates. In the next column over, we've got probabilities of exceedances of 0.2g. So pick that same threshold just for illustration, given a rupture. And we're computing this again using that Bohr, Joyner, Fumal 1997 model. And we can even see some familiar numbers, right? So and this is evaluated for the same magnitudes in the table rows here. So for magnitude 6.5, we had a probability of exceedance of 0.378. And for 7.5, we had 0.94, right? So those are the numbers from earlier in the video. We just evaluated the same thing for a bunch of other magnitudes as well. And then for each one of these possible magnitudes, we're going to take the product of the rate of the rupture times the probability of exceedance. Those were the two terms in our PSHA equation. So we'll take 0.10 taking that top row here, 0.0185 times 0.001. It's a very low probability of exceeding this ground motion intensity given that small magnitude earthquake. And we will get 1.59 times 10 to the minus 5 over here in the right column. Okay. And we'll do that marching through all these different magnitudes, and we'll get these tables over in the right column. Okay, and so we can see a couple trends happening now with these Gutenberg-Richter sources. If we look at the rate of the ruptures, the rates of the ruptures are going down, and they're going down pretty quickly because of the Gutenberg-Richter distribution. That a 5.1 has a 0.0185 rate of ruptures, and a 6.1 has a 0.008, right? So it's got about 1/10 of the rate of ruptures of the 5.1. The 7.1 has got 1/10 the rate again, and so on. So the rates are dropping off quickly as we move from large magnitude to small magnitude. But the probabilities of IM exceedance are picking up quickly, right? So the 5.1 earthquake is almost certain not to generate a 0.2 G spectral acceleration. As we move up to a 0.61, we're up above 10%. 6.5, we got a 1 in 3 chance. And once we're up to 7.5, we're almost certain to have an exceedance of the 0.2 G ground motion threshold, right? So the product of these two, as we look over here on the right, we've got pretty small numbers at the top. We got 10 to the minus 5s up here. And those numbers are small because of the ground motion model, right? That we've got 1% probability or less of causing an exceedance of the IM threshold. And then down at the very bottom, we've also got small numbers, 10 to the minus 5s. And that's because of the source model in this case, right? So the Gutenberg-Richter model tells us that it's pretty unlikely that we'll see magnitudes that big from this source, given the distribution of magnitudes that we see, okay? And then in the middle, we've got 10 to the minus 4s. And so at least order of magnitude, those are all bigger. And we see the probability in front going up and down by a factor of 3 or something like that. So somewhere in the middle is our biggest numbers, where the moderate magnitudes have the decent probability of causing an exceedance of the IM if they occur, and they're also decently likely relative to the rarer, larger magnitude earthquakes. Okay? So just a few qualitative observations here to set the stage for some calculations we'll do later, and build some intuition about what's going on. Okay, so then we've got all these terms over on the right-hand column, and then we're going to do the summation over all the ruptures, right, of those products. That was our last term in the PSHA equation back at the start of the video. So we just add up all these products, and we get this rate 0.00212 per year of exceeding 0.2 G spectral acceleration. Okay, and that's considering all the possible magnitudes from this source and their individual probabilities of causing an IM exceedance, given that they occur. Okay, so this was all for the case of 0.2 G spectral acceleration. If we repeat that calculation now for a 0.5 G spectral acceleration instead, the source model stays the same, the ground motion model stays the same. So it's going to be the same Board, Joyner, Fumal, 1997 ground motion model. We're just going to look at a different threshold. We can see some interesting things happen, right? So now we've got very low probabilities of causing an IM exceedance. So now we've jumped up a factor of 2.5 in ground motion intensity relative to the previous slide. So these small magnitude, like less than magnitude 6 earthquakes, have almost no chance of causing that strong of a ground shaking. Not absolute zero, but effectively zero here, right? And even the biggest magnitude earthquakes aren't certain to cause an exceedance of this strong level of shaking, but more likely than not. The rates of the earthquakes are the same, but when we take the products here now, we see a little bit different pattern on the far right. So we've got the products here now. We've got very small rates of exceedance from these because we're almost certain to have not exceeded the IM, even if they occur. And as we march down to the larger magnitudes here, we get bigger and bigger probabilities, and it looks like the biggest kind of products out of this calculation are somewhere down around here. And then we start dropping off just a little bit, but not completely down at the bottom. So we see now it's like magnitude 7.1, 7.3s that are contributing most to this summation when we get down to the bottom. And we get a smaller number here, of course, because each of these ruptures is less likely to cause an exceedance of 0.5 G. And so that's our result. And if we plot those out, here's a figure with those two numbers that we computed on the previous two tables. So we've got the 0.2 G and the 0.5 G values plotted in. And if we repeated that calculation for lots more IM thresholds, we could fill in a line here and get this full result. Okay, so that's our basic PSHA calculation illustrated through 3 examples of increasing complexity. We've now put in a range of ruptures. We had 15 ruptures considered in the previous case. And the basic idea is we just need to know for each of those ruptures, how frequently do they occur? What's their rate? And then what's their probability of causing the IM exceedance given that they occur? Take the product of those 2 numbers and add it up over all the ruptures. That gives us our ground motion hazard. And if we do that for multiple IM levels, we get this ground motion hazard curve. Okay, we'll stop there for now.